All right, so this is a joint work between me, Manas, and Lisha. This is a secure and automated scientific workflow. We call it SASW. So the idea came from looking at genomics workflows. So these are typically distributed. On the left, you have an example where people are looking at pathogen distribution and how the antibiotics are working against those pathogens. And they're looking at whether there are drug resistance bacteria that are emerging at different parts of the world. And as you can imagine, that this happens in a distributed scale, and these being more sensitive data, there are restrictions on whether these can be shared freely or not. Most of the time, these cannot be shared freely across different countries, but your benefit only comes if you collaborate on the both the data and the computation. On the right, things like the Emerge network, where all these universities and hospitals, they are sharing patient data and doing research on those. So a lot of these workflows are becoming a lot more collaborative. Now, if you look deep into one of these workflows, these can be multi-omics data sets. So they are DNAs, RNAs, cells, and you have your data. Then there are some sort of parameter files. Then the actual analysis that can be parallelized. So it can be a function that's looking at DNAs. There can be a function that's looking at RNAs, and there can be other things that you want to look into parallelly, and then generate a report from those. So this maps very nicely to a distributed approach. Your data and computation are geographically distributed. Now, the challenges are how do you match those computation with resource availability? All those universities we just saw, they might have different types of storage, they might have different clusters. More importantly, they might have different policies. So if you take an existing solution and say, I'm going to deploy this across different sites, that's not going to work very well, particularly because those would require you to have some sort of centralized control, either operationally or logically when it comes to security policies. So as we were working on this, we started thinking this might be perfect for a decentralized approach. So we have been working on building this peer-to-peer storage system called Hydra. And the idea was similar, where we said we are going to have all these different organizations, and we want to create a storage federation across them. And there is no centralized controller, there is no centralized decision making, so to speak. So here we take that idea and extend this to computation as well. And the second part of this is not only decentralized, but also having localized autonomy, right? So each university or organization decides what kind of computation they want to do, or what kind of data they want to share with others. So the challenge was, how do we enable this coordination without centralized orchestration? We did some prior work. We had a recent publication last year that talks about semantic naming from computation tasks. So the idea is you can take a computational job, and just like you name data, you can name them, and also map them to different computing clusters. And now the computing clusters might be running a named endpoint, a named service, something else. But the network should be able to map your computing tasks to those endpoints that are doing the actual computation. So that leads to this work. So this is the system overview of what we are proposing. The idea is we have these workflows, genomics workflows in this work. We convert them to a DAG, Directed Acyclic Graph, and then we break that DAG into multiple small segments. We'll see what that looks like. And then once we have that DAG, these nodes, they are creating this computing federation, so to speak. They can claim each of these tasks, perform the compute, and then publish the results. The interesting part is we don't necessarily need orchestration and synchronization between them. What we need is a data-oriented trigger. So we'll come back to this. Each of the tasks, they have their input, output, and what's the expected input, what's the name of expected data they're looking for. So for example, the first one, it's going to produce some data that's named. The second step, it's going to get triggered only when the data is available. So we can create this DAG, which each of the steps is dependent on the previous steps, and some of the steps might be dependent on multiple previous steps. But the whole process is not triggered by some central controller, but by the availability of data. So here, if we have a dependency on two tasks, as soon as two of the previous data sets become available, this task can continue. And that task can be claimed by any node that has A, availability of resources, and B, their policy can permit them to execute those tasks. So this is what I just said. Workflows are broken into tasks. Each task has semantic input and output names. They also have resource requirements and some sort of execution metadata. So if there are dependencies on external libraries, if there are dependencies on external data, those can all be annotated in the task. Now we have a task table, and the nodes learn of task via this task table. We maintain this a synchronized state between those tables. And the nodes can claim whenever a local resource, whenever a task becomes available, and then if their local resources and policies allow them to execute those tasks. Now, execution proceeds as the data becomes available. There's no centralized trigger. And then at the end, the result becomes available. The other aspect is we are still using federated nodes, just like we did in Hydra. And the nodes can belong to different organizations. There's no central controller. So they start by doing a trust bootstrapping. So each entity gets a certificate from a domain controller, a trust anchor. Then all the nodes and the data, they're named. And then we can do the mapping between name and our actions to have data-centric security, authentication, authorization, all of that. So where does this decentralization comes in? So we have task dissemination, right? So there's no global queue. All nodes, we have a synchronized state in form of the task table, but there is no global coordinator that's telling each of these nodes that node A needs to pick this task. That's the task claiming is done independently. Data publication, the tasks publish output under a predefined naming scheme. So they each of the output they would have semantic names, and that would trigger the next step of the workflow. And also the security is decentralized, right? So there's no central controller that's controlling trust between these nodes. So here is an example of data-driven task scheduling. So you have task Y, which is dependent on task X and Z. Now, when task X produces data X, it toggles a flag saying that data X is ready. Same with task Z, toggles a flag saying that data Z is ready. And at that time, task Y becomes ready. And the node in this example, node A, looks at the task table, says, oh, I see there's a task available for me to do, claims it, and then sends a notification to the other node saying that I have claimed this and executing this. And this continues until all the steps are done. Now, this is where we can do intelligent and decentralized scheduling, right? So we can say, can I put the task, the nodes can decide which task to perform. So they can say, and they can make their own heuristic decisions, right? So they can say, am I going to take this task because it optimizes the overall system performance? Am I going to take this task because it's nearest to the user who requested it? Or it might be some sort of policy-based decision, right? So you can say, I have geographical constraints that I cannot take this task. There are some subtle questions here. How do we know where these are coming from? But that's a research question that we can discuss later. So the task is done. Once it's done, it goes to long-term storage, which is again built on Hydra, and then there's a logging component to it that says this is how the task went. If it failed, why it failed, and we propose to train a model that. So first we convert the workflows to DAG some of the workflows manually, and so this is a starting point. And as we execute more tasks, we train a model that can automatically convert these workflows into DAG. We haven't done it here. It's still at a conceptual stage, but we think it's doable. So once we have that, the whole process is finished, and then the more jobs we get, the more intelligent that the whole module becomes. So what are the challenges and research opportunities, right? So the challenges are, how do we efficiently disseminate these tasks? So if we have a bunch of nodes who are claiming tasks, how do we make sure the whole system is performing efficiently? Conflict resolution, it probably would end up becoming a multi-objective optimization problem, as we saw in Hydra. Monitoring, who monitors these states? Probably it needs to have some sort of external monitoring. We're not sure what that looks like. And then the more distributed systems question is, how do we provide guarantees like safety and liveness for such a system? that would require more research, because if we take a DAG, we are placing compute everywhere, but how do we make sure the work is getting done and the users are getting the results at the end as they are expecting, right? So there needs to be some quality of service, not in quality of service networking terms, but in networking terms, but quality of service perceived by the user. How do we ensure that this system fulfills those? So I'll conclude with this picture again. It's a step towards truly decentralized computing workflows. So there's no scheduler, no controllers. We just need to have tasks, data, and nodes. We think this model enables flexible, secure, and large-scale scientific workflows, but we are just getting started. So if you're interested in collaborating, we'll really welcome input and suggestions. So with that, I'll open it up for questions.